Imagine building a massive waterway that cuts across an entire continent. The Panama Canal made it possible, but how did engineers overcome mountains, disease, and incredible logistical challenges? Stretching across the Isthmus of Panama, the canal revolutionized global trade and became one of the most impressive engineering feats of the 20th century. Completed in 1914, it connects the Atlantic and Pacific, drastically reducing the distance of ships traveling between the two, cutting out the dangerous and lengthy route around South America. The vision of connecting the Atlantic and Pacific had been a long-standing dream for explorers and traders back in the 16th century. The idea of a shortcut between these two great bodies of water was crucial, offering significant benefits. The traditional route around the southern tip of South America, the Strait of Magellan, took months and exposed vessels to harsh weather conditions and dangerous waters. The Panama Canal would be a revolutionary shortcut, cutting travel time between New York and San Francisco by nearly 8,000 miles. The first major attempt to construct a canal through the Isthmus came in the 1880s. The engineer behind the Suez Canal was the first to propose it. The French, inspired by the success of the Suez project, began work on the Panama. However, their efforts were plagued by severe obstacles, and the most significant of which were diseases like malaria and yellow fever. These diseases wiped out large portions of the workforce and caused issues for the workers. In 1904, the United States took over the project with negotiating a deal with Panama, which had gained independence from Colombia. The U.S. government under President Theodore Roosevelt was determined to complete the canal, but they had learned a valuable lesson from the French. One of the most critical decisions made by U.S. engineers was to switch from the original plan of a sea-level canal to a lock-based system. A lock system would allow for the canal to handle the significant elevation changes between the Pacific and Atlantic. The lock-based system involved building massive lock chambers that could raise and lower ships as they navigated through the canal, overcoming steep terrain challenges. The U.S. also learned from the French health issues, bringing in experts like Dr. William Gorgas to combat the disease and protect workers, ensuring the canal would be completed successfully. The construction of the Panama Canal faced some of the most formidable engineering challenges, primarily due to the region's difficult geography and environment. One of the most significant obstacles was the Panama's steep and mountainous terrain. The Culebra Cut, canal's deepest part, required the removal of a massive amount of earth, with the ground needing to be excavated down to a depth of 85 feet. This deep cut was essentially a massive artificial gorge carved through the continental divide, and the engineering feat required the use of powerful steam shovels and dynamite. Workers had to tackle an extremely unstable soil structure and deal with frequent landslides. The Culebra Cut alone required a removal of over 75 million cubic yards of dirt and rock, an enormous earth-moving task that would take years. Another major engineering challenge was dealing with the high elevation difference between the Atlantic and Pacific. The elevation disparity was about 85 feet, which posed serious challenges. To overcome this, engineers designed a series of lock chambers that could raise and lower ships. These locks helped ships navigate the steep slopes of the canal. Each lock chamber, made with reinforced concrete, was able to lift vessels over the high point of the isthmus and lower them back down. The lock system essentially functioned as a giant elevator for ships, allowing them to be raised up to the level of the Gatun Lake, and then lowered again. The process was both ingenious and essential to the canal's operation. To build the giant lock chambers themselves, engineers used reinforced concrete, a material that was strong and flexible enough to withstand the enormous forces at play. Each lock chamber was about 110 feet wide, 500 feet long, and 85 feet deep. The concrete was poured into molds on site, ensuring that it would be reinforced with steel bars to bear the weight of the pressure exerted by ships. The locks also were equipped with a system of culverts and valves that allowed the water levels to be controlled precisely. Water flow had to be carefully managed to avoid wasting too much, as the water used to fill and empty the locks had to be replenished continuously. One of the most critical solutions to a significant engineering challenge was the creation of the Gatun Lake. The artificial lake, formed by the damming of the Chagres River, provided a crucial water supply to operate the locks. The damming of the river created a reservoir that held millions of gallons of water, enough to supply the locks with the water needed. The Gatun Lake was not just a source of water, but also a buffer, preventing the canal from drying up during the dry season. The lake itself became a vital part of the canal's overall operation, as its water was used to fill the lock chambers and move ships through the system. The creation of Gatun Lake was an engineering marvel in itself, as it required the construction of enormous dams to hold back the Chagres River. The Panama Canal project was not only an engineering marvel, but an immense human endeavor. Workers were drawn from various parts of the world, including the U.S., the West Indies, and other nations. The decision to hire workers from the Caribbean, particularly from Jamaica and Barbados, was driven by the need for a large labor force, as most Panamanians were reluctant to work in such harsh conditions. Over 75,000 workers were employed at various stages of the construction, with a significant portion coming from the West Indies. These workers faced grueling hours, high humidity and sweltering heat, and physically demanding tasks like digging through mountains of rock, transporting material, and more. The environmental conditions in the Panama were harsh, and workers had to contend with tropical disease that plagued the region. Malaria and yellow fever were rampant, spreading quickly through the workforce. This disease was transmitted by mosquitoes, which thrived in the tropical climate, especially near the stagnant waters of the Chagres River and the marshy areas surrounding the canal. Malaria was a particularly severe problem. It caused debilitating fever and fatigue, severely impacting productivity. Yellow fever, though less common, was often deadlier and spread quickly through the camps, further exacerbating the situation. However, the situation began to improve thanks to the efforts of Dr. William Gorgas, a U.S. Army physician and expert in tropical disease. Dr. Gorgas played a pivotal role in controlling the spread of the disease, recognizing that the key to eradicating malaria and yellow fever was to eliminate the mosquito breeding grounds. He initiated large-scale sanitation efforts, draining swamps, fumigating areas with oil to destroy the mosquito larvae, and clearing vegetation where mosquitoes would typically breed. Gorgas' works in mosquito control greatly reduced the prevalence of these diseases, and his innovative approach saved countless lives. Thanks to his efforts, the mortality rate plummeted. Despite these improvements, the human cost of building the canal was still high. It is estimated that nearly 5,600 workers lost their lives during construction, a tragic toll attributed to a combination of disease, accidents, and the dangerous nature of the work. Many workers succumbed to malaria or yellow fever, while others died in work-related accidents, like landslides and cave-ins. In addition to the workers who lost their lives, thousands were injured or debilitated by illness. The construction of the Panama Canal involved groundbreaking engineering techniques. A monumental earth-moving task was required to carve a canal through the Panama's rugged terrain. This was achieved by using steam shovels, dredges, and railroads. Steam shovels could remove up to 15 cubic yards of material per scoop, while dredges deepened the waters along the route. A railroad system was built to transport material and workers, helping speed up the process. Reinforced concrete was used to build the canal's locks, ensuring structural integrity, while dynamite was employed to excavate rock, especially in the Culebra Cuts. The controlled use of the dynamite along with steam shovels allowed engineers to tackle the mountainous terrain and achieve a deep enough canal for large ships. The canal was completed ahead of schedule in just under 10 years, officially opening in August 15, 1914. This achievement marked the beginning of a new era in global shipping, revolutionizing trade by providing a shortcut through the Atlantic and Pacific. In 1999, the Panama Canal was officially handed over to Panama from the U.S., following the Panama Canal Treaty, which was signed in 1977. The Panama Canal Authority was created to oversee the management, maintenance, and operation of the canal. The ACP has modernized the canal's operations, ensuring that it remains a world-class shipping route capable of handling the ever-growing demands of global trade. Under Panama's stewardship, the canal has undergone continuous maintenance and upgrades to keep it in top shape. In 2016, the Panama Canal underwent a major expansion with the completion of the Panama Canal Expansion Project. This involved the construction of new, larger locks known as the third set of locks, designed to accommodate modern Panamax ships, which are larger than those that were originally able to pass through the canal. The expansion project also included the widening and deepening of the existing channel to accommodate the increasing size of global shipping vessels. The expansion has significantly increased the canal's capacity, allowing it to handle more traffic and larger cargo ships. From the mountains of Panama to the oceans of the world, the Panama Canal is an enduring symbol of what's possible when ambition meets engineering brilliance.